Okay, so we're gonna resume. So we'll go back to finish the first part of the presentation, but this is the hands-on part, and this is where it can get complicated if you really want to do the hands-on part. So if you want to use a laptop, set up the environment, it's good to start now so that you can install it while we are presenting further slides on what we're gonna do. So in terms of environment, so either you're familiar with Python, and obviously this will talk to you. So you will need some pip or Anaconda environment, some virtual environment that you can set up, and a Python interpreter. So if all of that does not make sense, you can use the Google Colab version. So I would advise, if you want to at least do that, so you can manipulate and hopefully upgrade to the local environment version. So I will just go through the steps of showing how to set up the Colab so you can start, for those who want, to set that up. So there's two things actually you can create. So do I need to explain what is Google Colab? It's just a hosted notebook. So if you don't know what a notebook is, it will take too much time. So you can just follow the lead. So the URL for Google Colab is colab.research.google.com. And if you want to get the tutorial, you can go to the GitHub repo here. So the same URL as before. Hopefully you can see it. And I need to find the so the icyn-tutorial.ipy notebook here that you can download. So you click on it. You don't need a GitHub account, actually, if you're really not familiar. And you can download here the raw file, the notebook. So okay, here it's trying to open something, but then once you have it, you just, when you're on Google Colab, you can select upload the file we just got. And you can just start the first two cells. So you just click on the arrow that will clone the GitHub repo and install all the requirements. And that part can take a lot of time if you're doing locally, because there's like 5 gigabytes required. So I'm not sure the Wi-Fi network here will be able to handle everyone. But it's pretty fast on Colab, so it should be just a few minutes. You can see it's already mostly done. So while you're installing, we're going to keep going through a few slides and we'll resume with the hands-on part.
So in few future slides, we are going to see what all components we build to make reinforcement learning work with our real platform. So I like to say that AI and automation goes hand in hand. Let me explain with an example. Like for a robotics use case, a robot needs a sensor to observe its surroundings, and to actually move the arm and leg, and to make the robot move forward, we need integration with machinery. So it's easy to build this brain of the robot, which will tell you how much an arm should move, how much a leg should move, but the brain needs to be integrated with all that machinery. So when it comes to integrating any AI thing with real world problems, it requires automation. So for that, one, for the provisioning of our test bed, we did some automation using Terraform, which is one of the infrastructure as a code technology. And we did automation for the scaling part. So to provision VMs in the cloud, we built the action execution module. And to collect the near real-time metrics of our test bed, we developed this data collection module. And like every other AI training, It requires monitoring, so we did monitoring using TensorBoard and weights and biases like tools. And one crucial thing which a reinforcement learning problem should have is this environment definition. So it's nothing, it's a Python script which is an interface to manage the RL environment as per the Markov decision process. So we are going to look more into details about these building blocks. So the very first step is to provision the test bed, and to provision the test bed we make use of this Terraform. So with the help of Terraform we deploy this access gateway and testers in the cloud. And the prerequisite is simple, we just need a cloud platform which could be flexible engine, GCP or AWS. And I think one question would come to your mind that we can use this provisioning in real time when training. So when the agent would decide scaling, we can provision the VMs as per the need. But here there is a bottleneck, which is this test bed, specifically access gateway and S1 AP tester. It takes around 12 minutes to fully configure and to be ready to serve the traffic. So this would become very impractical while training. So training time could increase a lot. So that's why we deployed few S1 AP tester and access gateway in advance, and while training we just activate and deactivate it. So scaling in our scenario is just turning off and turning on the VMs just to save the time and increase the training time of the agent. I mean, few of you asked about why not use containers. So Magma at that time was the state of the art for the packet core, and it was only supporting containers. But all of the process to integrate the RL will be similar for containers as well.
So if during training you remove this time that it takes to scale, wouldn't it learn a policy that then when you run it in operation and it does take that time to scale, then the policy would not be quite optimized to operation conditions? Because if you know you can activate very quickly, you will have a policy that probably scales up and down quite often. But then when you run it in operation, it will take time to scale. So then it's not learning in the same conditions as it will later run, no? Or
Well, actually, it depends how you handle those delays, because at first we did that during the provisioning, but we realized that it increases training time by a large factor, because it takes 12 more minutes each time. So it depends on how you tune your training, but basically, if during this delay you're not learning anymore, you could use the same model by switching, just saying, okay, we learn in a context where we just turn on and off, but we can use it in a context where we need to provision, but in this case we need to hold on during this time, maybe. But if it's not training anymore, I guess you can just use it. So it's a matter of tuning the model and how you handle the delay during the training and what kind of delay you will have during the real life. So I'm not sure there's one single answer to that. It really depends. But we could have used it, I guess, for and we didn't try that actually to provision the VM really with the train model to see if there was degradation or not. There shouldn't be theoretically, because.
right, yeah, I don't know if, I mean, the point here is to try to make sure that the agent knows that when it decides to scale, there is a time that it will take, and hence you cannot scale like all the time, right? So the agent needs to learn also this impact. I don't know if in the reward, let's say you scale up, but it takes a long time to scale.
I mean, what do you want the agent to learn to
understand that it has an impact. Deciding to reconfigure
The oscillations has an
a-
impact, or this delay has an impact? What is your question?
Yeah, I don't know. I mean, how to say, scaling up and down in a certain with certain technologies that take a long time to scale, you will learn a different policy that if you train with containers, for example, right? So the policy has to be different because the advantages of scaling up and down are different depending on the time it takes to scale up and down. So I don't know if that is how you encode that in the training so that the agent understands these aspects. I don't know.
You want me to answer? I do have an answer. It really depends because we are presenting what we've done. There's multiple ways to do it. There's no silver bullet on this kind of problem. So it really depends on how you handle this kind of action delays. So what we've done is one part of it is to hold on the training during that increase. So you don't collect metrics of something that is not, let's say, a situation where the environment is handling the traffic. It's you are scaling, so you stop. You put the training on hold during that time. That's one way to do it. Okay. So you're not training on the scaling moment itself.
I see.
So you integrate this delay in the training process. But there are multiple. There's a paper really focused on that part. That it's a very specific problem of this kind of environment, compared to a lot of problems that are usually used in reinforcement learning.
But in this case, just to clarify, what you do during training is that if you decide to scale up, you activate something that is there waiting, is already ready. So it's almost instantaneous to scale up and down, no?
It's not against instantaneous.
No, it's not instantaneous, but
when we activate and deactivate it, because again, VM, to turn on a VM, it takes time. To all of the network function takes time to start and be ready to serve the traffic. So again, delay is also here in this case.
So, but
that's a natural
instead of 12 minutes, it will take less.
2 minutes or 3 minutes.
I see. Okay.
It goes on with any real world system, I guess. I think that's not something which agent needs to learn. There is a concept in cloud called cooldown time. So we have to wait until a system is stable so that we can observe it. So that's not something agent.
So you still have a delay, but it's not. You reduce it from 12 minutes to like a couple of minutes.
Right.
Okay. Thank you.
Okay, to turn on and off the VMs while scaling, we developed this action execution module. So this action executor is a Python script, which makes use of the API provided by cloud to scale up or scale down the VMs. So in our scenario, the actions can one of these either to scale out, scale in, or to do nothing. So there are certain situations that requires the agent to do nothing. So it is just to maintain the current state of system as it is. So in our scenario, when we scale up or scale down, we scale up and scale down by you can see this access gateway and S1 AP tester mapping. So there is this one-to-one mapping between S1 AP tester and access gateway. So whenever we scale, we just scale by one instance. So there are some work in literature which says that, which also integrates this, that how many VMs should be scaled up and how many VMs should be scaled down. But just to simplify the problem for our scenario, we are doing scaling by just one instance. Other part is this data collection module. So the RL agent needs state as its input. So to form the state, we use this data collector module. It is again a Python script, and this data collector uses these two sources of data collection, which is orchestrator and Prometheus. So let's first see what orchestrator is. So orchestrator Orchestrator is the network management entity provided by Magma. So it is responsible for managing the life cycle of access gateways, and additionally it also provides a monitoring stack. So the orchestrator, being a life cycle management entity, also provides the Prometheus as its monitoring stack. And orchestrator collects the data related to subscriber or throughput or any other observation metric that a packet core can have. So there are some metrics, I think, which Guillaume mentioned in the scalability problem, which are not uh, present in the access gateway. So we created some custom metrics, and to monitor those custom metrics from access gateway, we deployed uh, our standalone Prometheus. So this standalone Prometheus collects the data using this Prometheus node exporter text file collector, and using these two data sources, the data collector aggregates all of the data and present it as a real-time state, which agent further uses as its input. So using orchestrator, uh, we collect the information about the connected users, the attach rate of users, and the CPU usage of access gateway and memory consumption of access gateway. And from our standalone Prometheus, we collect the memory consumption of network functions like MME, and the information about number of drop calls. So that's about the data collector part. And here, this is more extensive diagram from what we saw when we started the introduction with RL. So there is this same agent and environment interaction loop. So agent here in our case outputs one of those three actions and passes it to action executor. So action executor in further applies those actions in the cloud, and then we wait for certain amount of time for the whole platform to stabilize, and then we observe the state of the test bed, and we got this real-time state of the system, and by using this data uh, we formulate our reward, or we calculate our reward, and we also calculate our state. This reward is again goes as a feedback to the agent, and as a result of this action, the uh, environment transitions to a new state. So agent also observe the new state, and this interaction goes on until our goal is achieved or so. Any questions on this part?
So one thing I'm a little bit confused is with the one-to-one mapping between the tester and the access gateway. So let me understand. Let's assume we start with one instance. So we have one tester and one access gateway. We're running these, and so in order for me to observe something to decide to scale out, some event has to happen. No? Some new users have to come in. Something has to happen, right? Now these new users that come in, I thought this means that let's say like 100 more users come in. This would create another tester, or no? Where do I see that? Or in which component I see these new users coming in that will make me scale out to create a new instance?
I think it was shown in the previous slides where there was this workload generator. So workload generator sends traffic to all of the available testers. So that's one entity responsible for creating the traffic.
So when I have new users, I will have a new tester,
Yeah, that's what
activated.
agent will learn. So when we have the number of users increasing, the access gateway will be overloaded, right? And agent will be able to see that it's overloaded through the reward, and it will try to scale out, and it will learn the effect of that action.
Maybe just to clarify on what Chantal was describing, because I think your question, and the interpretation of the role of the tester. So
Yes.
the one-to-one relationship comes from the architecture of the software, and in Magma, that's how it's designed. Let's say with this tester part, the inode B has to be connected to one NME, and we create a new inode B each time. So basically, what happens is that the workload doesn't appear here because this is a pipeline reacting and the environment. So it sends traffic to what is available, and it load balances with what is available. And the decision to scale will come from the agent, and the agent will scale a pair each time. So you can see that as a single component. It's an architectural choice by Magma. We can change that. So it's a tester that will simulate the traffic, but the information, how much it should simulate at this moment, comes from the external component.
I see. So let me understand. So let's assume, again, we have tester 1, access gateway 1. Let's assume tester 1 is simulating 100 users.
Mhm.
And now I create the addition of a new 100.
Mhm.
At that time, the tester 1 will now create traffic associated to 200.
No.
No. And
If
so
you
so that the access gateway gets overloaded.
Let's say that at time t, you have 100 sessions and one tester and access gateway.
Yeah.
At time t plus 1,
I
you
get
have
2.
200.
Yes.
And the action that was taken was to scale out. So you
But-
have
but
now
wait.
2 instances.
But when I get 200, what component is loading the access gateway now with more CPU? Is that arrow from the tester 1 that now is sending more control traffic because I have 100 new
Okay.
users?
Yeah, because
Oh, no.
you don't have a network background, that's why. Okay, I understand the question. So at time t, we have the workload generator instructing the S1AP tester to simulate 100 devices.
Right.
So that it will be attaching, so not 100, but it will say that at this moment there's 5 new devices, so the total load will become maybe 100. So, and it will simulate 5 new attachments on the core, on the access gateway. At time t plus 1, let's say you have like 100 calls attaching right now.
Yes.
And the decision that was taken was to scale out. So now you have 2 instances. So what will happen is that the workload generator knows that at this time t it's supposed to generate 100 new sessions, and there's 2 instances. So what it does, it's try to load balance fairly between the 2. So it depends on the current status. So if there's already 100 on the first one, it will send all the new traffic to the new one. It's a least loaded balancing that we used.
Okay.
That makes sense?
Okay.
Oops.
So we obviously need to monitor our RL experiment, and in order to monitor it, we use TensorBoard, and in TensorBoard we track these crucial metrics, which is episode, reward, and reward accumulated at each step, and this one is the loss of our network. Okay, and maybe we can see from the episode reward that as the agent or our queue network learns, the episode reward increases. So that's a sign of that our queue network is learning something, and similarly the reward is also increasing, and the decreasing loss shows that the queue network is now converging, so it has learned what all environment has to offer. So this is how we monitor it, and this is steps per epoch, which just tells that what was the length of each episode. So we know that environment could crash, so the length of the episode can differ here, so that's what is shown, and there is this epsilon which is more concerned with the epsilon greedy policy, that these of policy methods used and the target network update. So the policy network and target network are copied. So how many times we have copied the policy network into target, that what it tells. Okay, and I think for the in order to monitor what we are giving input to the state, these are all the metrics that we monitor for from the test bed. So this is the average number of UE connected and the average UE attach rate, the average UE percentage, and one common pattern that you can see here is values are kind of saturating. So UE attach rate tends to decrease, CPU percentage tends to decrease, average users are increasing, so that's a sign of good learning, I guess. That CPU is optimized, number of users increasing, that's a sign of learning. And similar goes for this memory free and memory usage, so it possesses the same pattern. And we also monitor the call drops. Yeah. We also monitor the number of calls dropped, so we can see that nearly call drops has significantly decreased over the time, and VM count, you can see in initial phases there was lot of oscillations in scaling, and when the agent has learned the optimal policy, the scaling is more smoother now. So that's how we analyze and monitor our results.
These are the number of instances, no?
Yes.
It's adjusting. Okay. And the input, so these instances are adjusting to an input. The main input is what number of users. What is what you increase in order to force actions? Do you increase or decrease? What is the input?
These are
These.
our inputs, right?
Okay. So essentially, this is how you change the number of users across time. This one, no?
Yes.
Okay. This is not a result of an action. This is an external event, no?
Exactly.
The other ones are more results of actions, no? The CPU
So
percentage.
CPU percentage is result of the number of sessions connected. Attach rate is also linked to the number of sessions made each at every 5 minutes. That's
Okay.
This one is an input.
This
As
one
you
is
said, it's an input, but it's collected on the platform itself. So it allows us to measure if there's a difference.
Okay. And more or less during the episode, you essentially increase the number of users to see how you increase and decrease the number of users. You keep randomly.
We have a certain workload pattern in our case. So the users are simulated in a sine wave kind of pattern. So our load follows this sine wave pattern. So load is just an external factor, and these are the effect of the load, the CPU and memory. That's what we measure, and that's what agent observes, that what effect the load is having on the complete platform.
Okay. And when you put the CPU percentage, that is for how many instances or which instance?
No, we are not monitoring every single instance. We just average it out across all the instances.
I see. So this means depending on how many you have allocated, this is the average load you have on all
exactly,
of them. So if it's going down, you mean you have allocated enough instances to spread the load. Okay.
The assumption here is that the load balancing works, so the average should be approximately the same on all VM. But we could have used the input of all the available instances. That would be another way to monitor the state.
Right. Okay. But this is the average. Okay.
Yeah. And this is just simply the normalized value of what all we give input to the neural network. So essentially, this is the input to our Q network. And this board is just to monitor that we are properly normalizing our values. It's nothing more.
Just a side note, so this is not a course on reinforcement learning. It's way more complex than what we just introduced. So I included in the slide, and the slides are in the GitHub, some basic resources if you want to go further. So the main reference book is this one by Sutton and Bartow, and it's open source, so you can read it online and download it, but you can also buy it. There's also a course on that was given at Stanford and was recorded and is available on YouTube. So it's like 15 one-hour sessions, so a very nice course. Also one by David Silver, who was a professor at Stanford and did the first version of those slides. Also has a course recorded on his website, as well as a nice course and slides for this. And there's also a specialization on Coursera by Copol, Martha and Adam Wright from the University of Alberta, where David Sutton is too, I guess. Richard Sutton is. And also the bibliography of all the references we mentioned before. So this is in the slide. So going back to part 2, for the hands-on part, so if you're using a local environment, and I'm not sure a lot of people are doing it, but we can support you. And there's one laptop here where everything is already set up, so you can just use it if you want. There's only one, but I guess 2 people can use it if they want. Everything is already configured on it, so everything is downloaded, so you can use it if you want. You just have to use to plug it in because the battery is not so good. But it's here on the first row. If anybody wants it, don't hesitate. So the instructions are also on the GitHub. So that's basically what I said before. So if you're familiar with this command, you can just follow them. So clone the environment, create a virtual environment, activate it, and then you can install all the requirements. So that's what we done on the collab. We started before, so I need to restart session because it's been too long, and also because we have updated some libraries. So you want to go? So just to explain exactly what we'll be doing during the hands-on part, we're just going to introduce a little bit the abstraction. So we are not going to deploy Magma and network functions in the cloud due to a lot of constraints. So we're going to use some kind of simulation. So we're going to explain how it works. So that's basically the architecture of the environment. I'll let Shantanu explain that to you. And after that, we're going to manipulate it. So.
Okay, so this is the crucial component that any reinforcement learning pipeline should have. So this is which is called environment definition. So you can see the UML diagram over here. So this is the gym environment block, and the goal to have it is to have a standard interface for the RL training loop to interact with our test bed. So in order to develop this, we made use of one open source Python library which is called Gymnasium. So Gymnasium provides the standard API for the algorithms and environment to communicate, and it also provides some set of environments to experiment, like Cardpole or Atari games or multi-joint control. And this library is drop-in replacement for the OpenAI Gym library since 2021. So OpenAI Gym was the one who started this library, and now the maintenance and development has been taken over by the Farama Foundation, which is now called as Gymnasium. So we developed this Magma env. So again, this is a logical concept because it's a Python script, and it helps the algorithm to manage the environment while complying to Markov decision process. So let me just explain with the class diagram. So as the part of our automation, we have this data collector and action executor, which are again 2 Python scripts, and functionality of both of these automations are combined into this wrapper. So this is a wrapper over these two automations. So even with the help of this wrapper, we can take advantage of functionality of both of those classes. And this Magma env in turn uses this wrapper to implement the logic for the training loop to interact with the environment. So there are two crucial methods which are inherited from the gymnasium library, so which is step and reset. So what step function exactly does is, so step function accepts the action, so we pass action as the argument, and when we pass action as the argument, the action is executed in the environment, and as a result of that, this method returns a new state, and also returns the feedback of taking the action, which is also the reward, and it returns a Boolean value saying that whether we have reached the end of our episode or not, or to be more specific, as per our use case, it indicates that whether the platform has crashed or not. So, and one another attribute which is info, so it's not it is not used much in the training, just provide general information about the environment. So, and another method is reset, so it moves the environment to an initial state. So can explain it with an example. Let's say a platform is crashed in our use case due to the high workload. So in our situation, we can't make use of the test bed to make the RL algorithm learn. That's why we turn off all of the VMs and leave just one VM on. So we just again start from the beginning, where we have this one VM available to serve the traffic. And so we have this Telco core scaling env that we developed as a simulation to the Magma env. So this Telco core scaling environment, I guess, is not linked to any automation. So everything here is simulated. The load is simulated using mathematical formulation. The scaling and everything is implemented using some data structure. So I think Guillaume can provide more.
Yeah, so we're gonna move to the hands-on part. So this gym environment, Telco core scaling env, is the one that we probably will open source at some point. So that is what is on the GitHub right now. So that simulates everything. So it should make it faster and easier to do hands-on part, even if it's not that easy because of the complexity of the environment. So we already went through the installation of everything. So I will walk you through some examples. So you can either run the code locally. So basically you can do that. There's two configuration files that you can modify. So I'm gonna give some example before you do that. One is for the configuration of the pipeline and the experiments, and one is about the configuration on the environment itself, so what kind of platform we are simulating. And to run an experiment, so I'm going to show you just calling this script once you have changed the configuration. But also because we realize that it would be much easier to have an alternative in Google Colab, some of the parameters you can change by giving a command line parameter. So I will show you how to simulate that. If you're using Google Colab, you won't be able to see the animation that I will show because of the limitation of the environment. It will not display animation, but you can integrate it with the dashboards and see the metrics and the evolution of the training on the weight and bias page. So before we launch an experiment, if you want to see the progress of your training, you can create an account on weight and bias, as I said before. So if you don't already have one, you just sign up there So it's wnb.ai. It will ask you some information, sign up, so you can sign up with an email. And after that, it will ask you a couple of questions. So I won't go through the process, but it's very simple. Once you have it, you have an account, you will be able to go to your profile here in settings. There's an API key that you can copy. Sorry, I need to find it. API here in the danger zone API key, so you can copy it once you have created it. So if you have some trouble setting the account, you can ask maybe Gabriel, the support inside the room, to do that. You can also not have it and just say no when it will ask you to integrate your web and bias account while running. So let's start with the basic example we had before as a reminder. So that's not, it's here, the card poll example we had before, so I'd stopped here. So just to relook at the code that we had. So this was a stupid example in the sense there was no machine learning here. So we just had the training loop with as many episodes as configured. So here it was 5, and for each of these 5 episodes there were 200 steps for the training, and it was just calling the step functions that Chantal was just described with a random action that was taken about between all the available actions. And so that was the stupid part. So if we go to now the smart part, so I will first show you on my local environment what you can run, and then I will show you in Google Colab how to run the experiment. So once you have your environment, so it should be the same for if you're using the laptop, basically. You can, so I just change one parameter, this pipeline, okay. So basically what we are gonna, so the same pipeline can be used for multiple environments. So basically the pipeline is running the district-QN algorithm we saw before, but it's using the GIM interface abstraction to train. So we could give it the Magma environment, but also the card poll that we just had. It's just changing the subclass you're using. So that's a parameter that you can use. So you won't see the animation on Google Colab, but if you run the code from the GitHub, you can have the animation. It's just a parameter that you can use. And so there's a lot of things happening behind the scene here. So there's a lot of logs. So we can also see that. So just to illustrate, at the same time, it's uploading on weight and bias, so for the metrics of the training. So it does not make much sense for the card poll example, but just to show you that while it's learning, it's uploading. So I just need to find the right place. So yeah, so this is the experiment I just launched. So it automatically uploads to weight and bias. So this is not the Magma environment, so that we don't have the same metrics. So it's just to show that the code we're using is directly integrated and uploads in near real time on weight and bias, so you can see how it's performing. So just if we do that on an actual environment with an actual duration, let me do. So if you want to modify some parameters, there's this config pl YAML file, but there's also for the Google Colab some command line parameters that I will show you how to use. So you can define the number of steps and epochs, or episodes if you prefer. And we need to explain a little bit more the discrete QN maybe phases. So I'll go back to the slide. There's three parameters here for the duration of the training. So just to go back a little bit to what we said. So actually in this reQN there are three steps in the training process that we covered, but might be a bit blurry for you at this stage. So we mentioned the experience replay buffer that is required to have a sample of actions. So basically one of the parameters here, the minimum buffer size for training, will define how many steps then the process will collect information to build this buffer. So basically during that number of steps, so here 4,000, so that might be a bit long for our experiment, it will just do random action on the environment, not doing anything smart, just filling this buffer so it can be used for the neural network afterwards. So just this link to the replay buffer that is used by the district-QN algorithm. Then after that, and that's more something that you can see in, no, that's what I wanted to show, the epsilon decay phase. So there's what is called the exploration phase of the algorithm. So once we have this buffer that is ready, we have a first, the algorithm will start exploring the possible actions depending on the state, and it uses a parameter that is called epsilon, which will define how many random actions it will take, what is the probability of taking random action at each step. So it will start with a high probability, and that's one hyperparameter. So usually you start high, and it will stop at a very low value. So not zero, usually you still keep an epsilon value even during the rest of the training. But during this time, the epsilon value is linearly decreasing. Linearly, the probability of taking random action will decrease. So because the model is training. So that's the second parameter that you can change, either in the command line for the collab or here as a parameter if you use the config PR YAML file. It's the exploration phase here. So for 2000 steps here with this parameter, it slowly decreases the epsilon value. So you can also configure the values at the beginning and at the end of the training, but probably we don't have time to do that. And the third parameter about hyperparameters that you can play with if you want is the target update steps, which defines how often the target network will be copied in the training process. So back to the algorithm again. So in DeepQ network and this reQN afterwards, so there's those two network policy and target networks that are trained. So this is when the target, how often the target network is updated. So this is the last hyperparameter that you can select here. There's a lot more parameters in the file, but I'm not going to cover them. So for example, you can start a training with maybe a little shorter than that because we don't have that much time. 20 epochs of 200 steps, exploration phase should be okay. Maybe just put 500 here. So I'm going to start with those parameters, for example, and use the Telco core scaling. I think that's what I did. We'll see if it works. And I will show, no, okay. So let me check. What is the default one? Telco core scaling. Yes, no env. Okay. Core scaling. And I will show you now how to run that in Collab. So let me start it here. So I will let it run, so it will create a dashboard in weight and bias, and we can look into the training as it's happening. So if you want to run that in Google Colab instead, so if you have opened the eScene tutorial, and as I did before, if you run the first couple of cells, so the one that is cloning the GitHub, and the one that takes a long time to install all the requirements. So it should have asked you to restart the session at the end. So I already done it. So we don't see it because there are some updates that were done on the library version here. Okay, so yeah, it should ask you to restart session, so you just have to click here to do it, and hopefully you can run the experiment. So you can use those parameters. So S is for the number of steps, so 200 steps per episode. Dash E is for number of episodes or epochs, so I put 20 here. B is for the buffer size, so 2000 actions in the buffer. X is for exploration time, so this is the duration of the epsilon decay, the linear decrease. And T is the time between two copies of the target network to the target network. So hopefully it should work. And if you want to run another environment like cartpool, you can use cartpool like this. Capital E, cartpool. But you won't see the nice animation because of limitation. So I'm just going to run the default telco core scanning, but I think it should be the default one. So you should see the logs appearing, hopefully. Okay, not so bad. And so since it's the first time we're running it, it will ask you if you have a weight and bias account. So if you have already created it, you can use interface E. So you click here on enter your choice. You can, so if you want to skip that part, you can just put input 3 here. So it won't upload anything, but you can run the experiment, but you won't see anything. But if you have a Google weight and bias account, you can get the API key. I showed you before. So, but if you want to, you can skip it and you just put 3 if you're not confident. So I will put here 2, and I will input. If you already have 1, so you select 2, and it will ask you for the API key. So you can paste it here, and it will upload it and running the experiment. So the logs are not very important. It's just some logs. But
Is it free?
wait and there's probably a paying version, but the free version is enough. And I'm using the free version here. Otherwise, there's a tensor board that is also created, but you can't access it with while running it on Google Colab because it requires a local server and so on. So weight and bias allows us to show you, and you can see it while running it in Google Colab. But otherwise, you can connect to the tensor board. You will see the same dashboards anyway, but it will be local. Nothing sent to the cloud provider. 200 steps. So there's only 20 episodes. Maybe that's why. So let's put the default. It was 4,000 here. It was 50. 500 episodes, yeah. And 20 steps? 200. It's a bit like this, okay. Let's try to rerun it. So yeah, if you input parameters that's not gonna sometimes give very good results. So basically here that means that the episodes were pretty short. As we can see here, steps per epoch means that, so I'd put around 50 episodes, like 200 steps per episode, and it never went further than 40. So it stops after the number of epochs. I asked him to, but it was never able to complete a full episode. So that means that crash happened. So we need to have more epochs, so it will learn a bit more. So let's run this experiment. So I'm running a longer experiment to try to show you the logs as we are going through them. So the one I just started. So maybe just to try to re-explain what is happening during the training. So in the dashboard, so if you want to set up like a reinforcement learning pipeline for this kind of environment, so what we put in the dashboard that Shantanu has already explained. So this is just showing the current step. So it's a linear function showing that it already trained for 2000 steps. And here we can see the number of epochs, the steps per epoch. So for each epoch, how many steps were possible, and epoch steps. So that's not very interesting, I guess, to explain. So as the parameter we put was like to have 4000 as the size of the replay buffer. So that means that after 2055 steps, we are still filling the replay buffer. So the reinforcement learning itself has not really started. We need to reach 4000 steps. So it will start the epsilon decay phase, this exploration phase. So far it's just doing random action, filling this buffer. So this is, I could have a shorter one, but what I can show you too, if you want to play, maybe not right today, but as part of the, I can show you on GitHub, that will be maybe easier. The reward function that is being used for the telco core scaling environment, you can see in GitHub, so let me open the right file. So this is a full path here, telco core scaling environment helpers reward wrapper. So this is the one that we had put for this experiment, and this is one, probably the one from the paper I mentioned at the beginning. So this is the one that is used if you're using this environment. If you're using the card pool or any gaming environment, it will be using the reward function that is defined in this environment. So if you want to modify the reward function, you can modify this file. So this is a Python function. Probably not today because we have a limited time, but just to explain a little bit what we have here. So basically we are looking into the state, what we call the number of calls dropped. So we use this term, but maybe we haven't defined it clearly. Basically, it's the difference between all the sessions or calls that we are trying to establish and the ones that are actually established. So because we are generating the traffic, we know how many we're supposed to see, so we can compute the difference. So that means that's the degradation of the service, basically. So if it's high, if we have any call drops, then we have a negative reward, and which will be based on the actual number of calls dropped. After that, if there's no call drop, we are trying to have the memory usage. This is MME service of Magma, below 70%. So we'll have a positive reward if it's lower than that, based on the actual value. Otherwise, we'll just take, that means we are above 70%, so we have a negative, again, reward to steer the training to not go beyond this usage. So that's one way to do it. And we just have like a maximum, well, a minimum value for the reward, which is -10. So here in this case, our reward function goes from -10 to at most 1 if we have currently 70% of usage of memory for the MME service. So that's the values we can have here. But you can, one of the important aspects in reinforcement learning in the design is to select the appropriate reward function. So this is just an example. There's plenty possible ways to do it. It really depends on the infrastructure and environment that you are using. So that's just an example. So you can change it if you want. So if we look at the matrix now, so it went a bit further. So 6,000 steps now. So it's so the 4,000 steps for the buffer filling are done. So I guess I need to maybe update because we have new dashboards. And sorry. Sometimes weight and bias doesn't fully update when there's new metrics that it's supposed to show. Okay, so now we can have them. So here you can, so it's not a tutorial on weight and biases, but you can see the RL parameters evolution. So maybe you start with the epsilon that Shantanu has shown. So we see that the 2000 steps of epsilon decay, so it started after 4000 steps when we had the buffer filling, so you can see 4000 here, and hopefully on your own test. And it was a linear decrease for 2000 steps, so that's what was done until the 6000 steps. And since so the epsilon value is now 0, 0, 1, 1, 10 minus 3, something like that. And we can see the learning parameters. So the episode reward, it should be increasing, so it's not that good here. Let's say we didn't see that. And the loss is decreasing, so that means that the Q value that is computed is closer to the best value, I would say. And there's also some system metrics that are monitored. So we are not using them for the reward function or whatever, but you can actually connect any kind of metrics you want here. Okay. So any question on that? Because you can run it, the GitHub will remain open, and hopefully we will make some part of it more open source in a more official arranged way, but we have to go through a process for that. And once again, you can run any kind of environment. So now landing, I think. So you can actually select, there's a few of them that you can see in the Lunar Lander, I think. Lunar Lander, sorry. Just to show you a fun one. So the same algorithm, but for different things. Yes, Kurt. Okay, sure. Okay, timing, okay. Oh, yeah, okay, that's what I had in mind, okay. No problem. So just the same algorithm, because we are using the GIM interface, it can be used for any kind of environment. So here it's another example from the Atari games. So you see that, well, so far it's not very good. But hopefully it will get better. So I'm not sure we have time for it to get better. So it takes time to train reinforcement learning. So just for information, to do the training on the actual platform takes a full week, at least, to have something that start behaving naturally. Yeah, for the real platform, not the GIM, not the simulation, but the Magma platform. Yeah, almost 1 week. Wow. Yeah, it takes a bit of time. But because of the parameter we use, so we are exploring, there's ways to improve that, but just using this reqn as we described, it takes 1 week. There's a way to make it a bit shorter, but that's sure. Sure.
In the metrics is the episodes. How do we see the what you were showing? Okay. It was a function of the steps.
Yeah, yeah.
Is that one episode or?
It actually depends on the metrics, so that can be a bit confusing. You're right. So here.
Also, I don't understand what the epoch is.
So epoch is episode. Sorry, we use the two of them interchangeably. The same thing.
Okay, perfect. Okay. And
so an epoch or episode is, like, if we take the game analogy, is the duration of the game. So game over or you win. A step is a number of steps you take in one single episode. So depending on the figure, actually some of them use the number of steps. So this is the overall number of steps, so across all episodes or epochs.
Because there was how many steps per episode?
In the test I started, let me check. It was 200 steps and 500 episodes in this test that I'm showing here.
Okay, so 10,000 steps.
So you can see steps per epoch. So this is not learning very nicely. I don't know why. So this is a demo effect, I guess, because it should improve. So maybe let's show on the slides. It was better on the slides. The steps per epoch. Okay, so we should expect something like this. That's not what we were seeing. So I don't know what I got wrong. But if we have 200 maximum steps per episode, it will stop. Sometimes it should, and eventually during the full training, it should get more and more to that maximum.
Closer to the 200, but it can
And-
stop earlier because of crashes.
Yes.
Okay.
Yeah, that's the reset. And this is specific of the problem because in a game, of course, it's easy to know when it's finished. It's you win or lose. Here we have an infinite horizon. It should be keep going. So we have to put a figure for the training, but it's a bit artificial. That's one hyperparameter that you can use.
Okay, so then in the second one, when you see the epsilon as a function of the number of steps,
Sure,
Then-
there's this one. Yeah.
so where do we see does it mean that the first episode is epsilon is very high, the second episode then, so these also
So
is a function of episodes here, no?
It's a function of steps actually, because we
Right.
have like 500 episodes. It's a very limited number of episodes, but you have, if there's 200 episodes per steps, you will have 200 by 500, so 100,000.
So this means that the first episode, the epsilon tends to be very high. The second episode,
Yes,
It
it
keeps
it's
going. The
slowly.
third
Yes,
episode-
it's a linear decrease. That's the way the algorithm has been designed. So probably there are people thinking of other strategies, but it's just saying, okay, at the beginning we will test all random action,
yeah.
and slowly we'll use the policy-defined
Right.
actions
But I thought this is not for every episode. This happens
at the
Uh,
beginning only.
at the beginning. So the first episodes are more exploration. The later episodes are more exploitation.
Yes.
Okay.
Correct.
Do you don't do exploration, one episode, then you do again?
Not this one.
Okay,
Not
okay.
this
So
algorithm.
this is okay. This
And
is
the
across
value is not
multiple
0 at
episodes.
the end. It's 10 to the power of minus 3. 0, 0, 0, 1.
Okay.
Just to have a minimum exploration still. Just to make sure that we are not stuck in some local optimal, and that's better action to explore anyway.
I see.
Okay, so we have to conclude eventually. So just a few slides to finish. It's for me, I guess. Yeah, we'll see. Thank you for the questions. So we can take question afterwards, of course. So just feedback on the actual training on the platform. It's part of the paper I mentioned before. So I just show you in the code the reward function that was used. So we don't use all the metrics available. That's part of the tuning process, depending on the platform you're using, the algorithm also you're using, but the reward function probably is one of the main questions you should ask yourself, because there are plenty of algorithms available. We just showed discrete-QN, but we also explored others. But the reward function is an important aspect. And, sorry. I don't know why. So let me. So the actual figures from the actual Magma training here. So we compare to a threshold-based approach that I mentioned before. So we scale in when we are above a threshold, and we scale out when you're above a threshold, and scale in when we're below some other threshold. So here we are showing the number of sessions dropped, so the quality of the service, let's say. So we can see there's a lot of codes drop because the load we are injecting here is a sine wave based. So there's a lot of changes of the threshold, so it's not very good for a threshold based approach. If you look at the discrete-QN, so there's two scenarios here, with and without action masking, but basically we can see the first part with the buffer filling random action. So this is very similar to what we have with threshold based actually, because we are not optimizing anything. But we can see that after the exploration, so we have the exploration between 4 and 6,000 here, the model is becoming pretty good. We have a bit of difference with action masking. If we look at the pure numbers, we could see that if we just look at the last phase, once we have done the buffer filling and epsilon decay, we just put the figure for information, but the most important part are the last 3 lines here, to comparing the 3. So for 4,000 steps, it took 34 hours to train the model, so that's not really a week, it's shorter. But if you include the whole part, it was 187 hours, so that's the whole process. And you could see, so the main metrics is this, so the number of codes drops, which was 2 orders of magnitude lower than the threshold-based approach. And a bit of improvement by using action masking method.
When you say the time it takes to train, is it how do you define the time when it finished training? It's conversion to something, or you define
yeah. So basically, you could say that the training is done after the exploration phase, but it can still improve in this example because we still have a small value for epsilon, so it can still improve. So, but basically, the last part is a train model. That doesn't change a lot.
So the 187 hours is how many episodes and how many steps is a lot of.
It was for. Do you remember how many steps it was? It's 10,000 steps. It's written actually, and the duration of episodes. How many steps per episode? Do you remember? Yes, but the maximum we had, do you know? 200, yeah, around 200 probably is the maximum number.
Okay. So the time is proportional, is proportional to the number of steps, no?
Yeah, sure, and also it depends on the actions that were taken actually. Because the threshold-based, you can see, has a very long duration for less steps.
Yeah.
It's because it's taking a lot of actions, and each action takes time if you decide to scale in or out. So it's like 2 minutes after deciding that we just simply turning on and off. So
it
the
also
more action
takes
you
into
take, the longer it
account-
takes to train. It's not completely linear.
I see. It's taking into account the time it takes to perform the action also
It's
here.
a whole duration
Okay,
that
I
it
see.
takes to run the experiment.
Okay.
It's not just the training part. Because it's live traffic that we're injecting, so the learning is done on live traffic. So that's why we have simulation environment to try to fine-tune that without using a platform 1 full week.
Okay. Yeah. Another question is: you
Sure.
could
We
train
have time.
this, and then once it's trained, now you could test it directly with epsilon equal to.
Yeah. You can use a train model and
Once it's
use
trained,
it in production.
you can compare
afterwards.
to the threshold policy, and in that case, you would not have that initial
Sure.
phase where things go all up and down, right?
That's this last part, because on the last part, pure exploitation, epsilon is already minimal value.
Okay.
So we're just comparing the two. The first two parts are not really useful because, it's the learning part. So it's doing random action, so it shouldn't be good. But actually, it's not that worse than the threshold-based because there's a lot of fluctuation.
Right.
It's just for information, but we can see that it improves if you take the whole process or just the last part with the train model. You can see that the last column with the dropped calls is much lower.
Much
So
lower.
you can see it's improving. It's
That's what I
learning
was
something.
wondering. Okay, that makes sense. Thank you.
No problem. Any further question? Don't hesitate. We can do that during lunch break too. Okay? Okay, thank you. Thank you, everyone.
So thanks a lot for the tutorial. I think a great insight. What's going on, very hands-on. That's not that easy.
No.
Eventually not typically very flashy in some way.
Yeah.
But I think on the other side, technology sometimes should disappear and the usage of technology is more in the foreground. And that's sometimes where we struggle to...
in networking, it's not easy to show some results.
Right, good.
Not very
But,
spectacular.
but nevertheless, I think you did it very, very well. Thanks a lot for being here, for doing this, giving an insight into this very upstarting topic. And I think it becomes more and more important and hope that we see these technologies more around here. Thanks a lot.